From Dust to Stars, The Formation of Stellar Systems. Title: From Dust to Stars, The Formation of Stellar Systems. Introduction. The formation of stellar systems is a fascinating process that brings to life the birth of stars and the planets that surround them. It is a celestial ballet where gravity plays the lead role, orchestrating the intricate dance between dust particles and gas clouds in our vast universe. The role of gravity. At the heart of the star formation process lies gravity, a fundamental force that shapes the universe. Gravity pulls together clouds of gas and dust, causing them to collapse under their own weight. As the gas cloud collapses, it heats up due to the immense pressure. Eventually, this leads to the formation of a protostar, the early stage of what will later become a fully fledged star. Protostar formation. At the center of the collapsing gas cloud, a dense core emerges, known as a protostar. This core continues to accrete more gas and dust from its surroundings, growing in mass and density. As the protostar continues to accrete material, its temperature increases, eventually reaching a critical point where nuclear fusion ignites within its core. At this stage, the protostar becomes a main sequence star, like our Sun. Accretion disks and planet formation. Alongside the protostar, an accretion disk forms. This disk consists of the remaining gas and dust that did not fall onto the protostar. Over time, the particles within the disk begin to collide and stick together, forming planetesimals, the building blocks of planets. Through further gravitational interactions and accretion, these planetesimals grow in size, resulting in the formation of planets. The composition and location of these planets depend on the initial conditions and properties of the accretion disk. Feedback and stellar winds. As the protostar evolves into a main sequence star, it emits powerful stellar winds and forms bipolar outflows. These outflows carry away angular momentum and excess material from the protostar's immediate surroundings, preventing the formation of additional stars in close proximity. These winds also disperse the remaining gas and dust from the protoplanetary disk, influencing the final composite. Ion instability of any planets that have formed. Multiple star systems. In some cases, the collapse of a gas cloud can give rise to multiple stars instead of just one. This occurs when fragments of the collapsing cloud break off, forming separate protostars within the system. The manner in which these protostars interact can determine whether they remain bound together as a binary or multiple star system or if they become unbound, each going their separate ways. Role of stellar feedback. Stellar feedback, such as the powerful radiation and energetic stellar winds from massive stars, can have a significant impact on the formation of stellar systems. It can disrupt nearby gas clouds, halt or trigger star formation, and even influence the formation of massive stars themselves. The interplay between the radiation and winds from newborn stars and their surrounding environment is a complex process that shapes the dynamics of stellar systems. Evolution and lifespan. Once a star reaches the main sequence phase and maintains a stable balance between its gravity and internal fusion reactions, it settles into a long, relatively stable period. The duration of this period depends on the star's mass, with more massive stars burning through their fuel reserves at a faster rate. Ultimately, all stars exhaust their nuclear fuel, leading to their evolution into different stellar remnants, such as white dwarfs, neutron stars, or black holes. Stellar evolution and supernovae. As stars age and consume their nuclear fuel, they undergo a series of changes known as stellar evolution. The specific path a star takes depends on its initial mass, with more massive stars undergoing More dramatic transformations. For stars like the Sun, they expand and become red giants before shedding their outer layers and leaving behind a dense core called a white dwarf. However, for stars much more massive than the Sun, their fate can be more explosive. These massive stars reach a point where they can no longer sustain nuclear fusion and undergo a catastrophic event. Known as a supernova. During a supernova, the star explodes, releasing an immense amount of energy and producing elements heavier than hydrogen and helium in the process. These elements are then scattered into space, eventually becoming the building blocks for future generations of stars and planets. Clustered star formation. Stellar systems are not formed in isolation but often within clusters. These clusters contain numerous young stars that form from the same gas and dust cloud. The gravitational interactions among the stars within the cluster can affect their formation and evolution. Sometimes, close encounters between stars can result in the exchange of material or even the merging of stars. These interactions see and shape the properties and characteristics of the stars within the cluster. Observing stellar nurseries. Stellar nurseries, also known as stellar birthplaces, are regions of space where stars are actively forming. These nurseries are often found within large, dense clouds of gas and dust. Astronomers use a combination of telescopes and instruments to observe and study these regions in different wavelengths of light. Open questions and ongoing research. While significant strides have been made in understanding the formation of stellar systems, many questions remain unanswered. For example, the exact mechanisms that trigger star formation within a collapsing cloud are still not fully understood. The role of magnetic fields and turbulence in regulating and shaping the collapse process is an ongoing area of research. Furthermore, the formation of giant planets, such as Jupiter and Saturn, presents its own set of challenges. The rapid growth required to form these massive planets within a relatively short timescale is a puzzle that scientists are actively working to solve. Exoplanet studies and detailed observations of young planetary systems offer valuable insights into these processes. Stellar feedback and star cluster dynamics. In the formation of stellar systems, stellar feedback plays a crucial role in shaping the surrounding environment. Stellar feedback includes the radiation, stellar winds, and energetic events like supernovae, which can have a profound impact on the surrounding gas and dust clouds. These feedback processes can trigger the collapse of nearby gas clouds, leading to the formation of new stars. Furthermore, stellar feedback can influence the dynamics of star clusters. In clusters where stars are born close together, strong gravitational interactions occur. These interactions can lead to the ejection of low-mass stars from the cluster or the exchange of material between stars. In some cases, these interactions can even result in the formation of binary star systems. Chemical enrichment and the building blocks of life. The formation of stellar systems also plays a crucial role in the chemical enrichment of the universe. During stellar evolution, stars fuse lighter elements into heavier ones, producing elements essential for life, such as carbon, nitrogen, and oxygen. These elements are then scattered into space when the star reaches the end of its life cycle, enriching the surrounding gas and dust clouds. These enriched clouds become the birthplaces of new stars and planets. The presence of these heavier elements in the protoplanetary disk can influence the composition of planets and potentially provide the necessary building blocks for life to arise. Understanding the chemical enrichment process in stellar systems is essential for unraveling the origins of life in the universe.